So the motivation for introducing entropy-regularized optimal transport was to have the ability to compare probability measures in a meaningful way, whether these distributions are continuous, discrete, or a mix of both. And the need to compare probability measures arises in fairly often in machine learning applications. So I'm going to give you a couple of motivations. The first setting here is the discrete setting, and the problem we consider is quantization. So imagine you have a large point cloud here, which is represented in orange, and you want to find a summary of this orange point cloud, which is going to be represented here by this blue point cloud. And so each of these point clouds are actually discrete measures, so empirical measures that are just a sum of Dirac's in these points. And your goal is to minimize some notion of distance here, d, between these two point clouds. So minimize some notion of distance between these two empirical probability measures. And in quantizations, you want to minimize this over the positions of the blue points so that the blue points are going to represent your larger data set in orange in the best way possible. Another setting here would be semi-discrete. So you have your point cloud, again, here, which has a known distribution beta. And you want to learn some parametric model alpha theta, such that, again, some notion of distance d between your data set beta and your model alpha theta is going to be minimal. And so you want to minimize over the parameters of your model theta until you find the optimal parameter that so that your model alpha theta is going to fit your data in the best possible way. And so in both of these examples, I said we want to minimize some notion of distance between the point clouds or some notion of distance between the model and the data. But the question is, what is the right notion of distance to use in these problems? And so for that, I'm going to start by reviewing some common notions of distance between measures. So probably the most widespread notion of distance in statistics are phi divergences that were introduced by Caesar in the 60s. And for that, so if you want to compare two probability measures, alpha and beta, you choose some convex function phi, and then you're going to compare your measures by looking at their ratio through that convex function phi. And the one that people use the most often, I guess, is the Kullback-Leibler divergence, which corresponds to having phi of x equals x log x. And so you're going to compare your two measures by looking at the log of their ratio. And you can see here in this definition that as soon as alpha and beta have disjoint support, the log here is not going to be well defined, and your KL divergence is going to be equal to plus infinity. And so I'll explain to you in a very simple example why these phi divergences are really bad notions of distance to use when you're trying to learn measures. So here, it's our example, you have a Dirac in 0 and in blue, and then you have another Dirac here in orange, which is at 1 over n. And so you have this sequence alpha n of Diracs at 1 over n, and you can see that as n increases, your Dirac, your measure alpha n, in some sense converges to the measure alpha 0, right? It's so that's the start, and then when n increases, it's getting closer in some sense. But if you look at the KL divergence between alpha n and alpha, it's always equal to plus infinity because, again, these measures have disjoint support. So you can see that we want to be able to have a notion of distance that tells us that these measures are getting closer, right? If you are taking the gradient, for instance, you want your gradient to be able to pull you through that to that blue measure, and you don't want to have no signal like it's the case here. And so the formal mathematical notion behind that idea would be the metrization of weak convergence. So we say that a sequence alpha n weakly converges to alpha if the integral of any continuous bounded function against alpha n converges to the integral of that same function against alpha. And we say that a distance between measures, d, is going to metrize weak convergence if if convergence in the weak sense is equivalent to convergence in the sense of that distance. And so KL divergences, and most generally phi divergences, don't metrize weak convergence. And so we're going to introduce other notions of distance that have the ability to metrize this weak convergence. So an alternative to phi divergences are integral probability metrics. And for that, you choose some class of function f, and you're going to define your distance between alpha and beta as the supremum over all functions in that class of the average of the expectation of f under alpha minus the expectation of f under beta. So you're going to look at the maximal gap between the expectation under alpha and the expectation over beta for that class of function. And depending on the class of function that you use, it's going to be a weaker notion of distance. And it covers the several well-known distances as well. So if you take f to be the class of functions upper bounded by 1, it corresponds to the total variation, which does not metrize weak convergence. But if you take f to be the set of 1 Lipschitz functions, you get the 1 Wasserstein distance, which does metrize weak convergence. And if you take f to be the set of functions that are upper bounded by 1 in the RKHS norm, then you get maximum mean discrepancies. And that I'm going to tell you a bit more about that. And under some assumptions, MMD also metrizes weak convergence. Right, so to understand maximum mean discrepancies, you first have to be a bit familiar with the notion of reproducing kernel Hilbert space. And so I'm going to recall the definition here. So we say that a Hilbert space H is a RKHS if you endow it with a kernel function k, which is going to be positive semi-definite function. And so for H to be an RKHS with kernel k, you first need this kernel k to belong to the space, to the Hilbert space H. And also the key characterization of these RKHS is that every function in the Hilbert space, so if you take any function f in that Hilbert space, it can be represented as the scalar product of a representer f against the kernel function k in the sense of the scalar product in that RKHS. So this is a very convenient representation of functions because you can always decompose them as scalar products against your kernel function. And so the definition of maximum mean discrepancies is this integral probability metric that I introduced earlier, but where you take your functions to belong to the unit ball in that in the sense of this RKHS norm. And so here is the definition of the integral probability metric. So you take the supremum of all functions in your RKHS and you look at the gap between the expectations and over alpha and beta. And thanks to this characterization of functions in the RKHS, so you can rewrite them as this scalar product with the kernel, then you can actually write this soup in closed form and you end up with just this very simple formula at the bottom. So it's actually just the sum of 3 expectation over product measures. And so you can see that if you take, if you have samples from alpha and beta, you can just estimate MMD by replacing these expectations with empirical expectations, and the cost of each of these terms is going to be n squared if you have n samples from each measure. So MMD can be very efficiently estimated from samples. Another notion of distance that is completely different is based on the notion of optimal transport that was introduced in the 18th century by Monge. But here we're going to focus on the later formulation by Kontorovich from the 40s. And so to define optimal transport between 2 measures, so here it's represented in the discrete setting with alpha and beta, you first need to choose some notion of cost C, which tells you how much it costs you to move a unit of mass from a point X in the first measure to a point Y in the second measure. And so in general, it's taken to be the Euclidean distance, but it can be any other notion of distance that best suits your problem. And so once you have defined that notion of cost C, you're going to look for the best coupling, so which here is represented as a matrix pi, and the coupling pi of xy tells you how much mass you move from a point x in alpha to a point y in beta. So for instance, if you take that point here, you look at the correspondence in the matrix and tells you where you send the mass to the second measure. So this coupling pi really gives you a correspondence between your 2 probability measures. And the optimal transport cost is going to be the minimal cost of transporting the mass alpha to beta according to the optimal coupling pi. And so formally, you need to solve a minimization problem here. So your optimal transport problem consists in minimizing over all product measures with marginals alpha and beta, the integral of your cost with respect to that coupling. So it's the total cost of moving the mass from X to Y, from alpha to beta, according to your optimal coupling. And this minimal cost is actually what we call the Wasserstein distance, when you take the cost to be some power of the Euclidean distance. And the Wasserstein distance is an actual distance between measures. It satisfies all of the axioms. And it does metrize weak convergence also. So let's see what are the pros and the cons of using optimal transport versus MMD. So the first thing to consider is the sample complexity. So I'll get back to sample complexity a bit later, but intuitively, it tells you how well you can estimate a distance between measures by computing the distance on samples of these measures. And so how fast the empirical distance converges to the true distance. And for MMD, this rate of convergence is 1 over square root of n. So it's a nice convergence rate, not dependent on dimension. But for optimal transport, your convergence rate is going to be n to the minus 1 over d. So you can see that as the dimension increases, your convergence rate is going to get worse. And so you suffer from a curse of dimension when you want to compute optimal transport with samples of your measures. So that's the statistical perspective. And then, of course, we have the computational perspective. So if we're given 2 samples of size n of our measures alpha and beta, and want to compute the empirical MMD or empirical OT between alpha and beta. For MMD, so if you recall, MMD could be written as the sum of 3 expectations of product measures. So each of these product expectations over product measures in the empirical case is going to be a double sum, so it costs you n squared. While for optimal transport, you have this minimization problem over couplings that has 2 constraints, 2 marginal constraints. And so for this, you need to solve a linear program, and this is going to cost you n cube log n. So you can see that from both the statistical standpoint and the computational standpoint, MMD is favorable. But then, of course, you want to see how these 2 notions of distance perform on an actual learning problem. So here we consider the simple example of quantization that I showed in the introduction. And here we actually have the same number of points for the blue point cloud and the orange point cloud. So the minimum is just going to be having the blue points cover the orange points. And we're going to see how this thing works when we're doing the minimization problem with 2 different notions of distance, the first one MMD and the second one optimal transport. So for MMD, yes. So for MMD, of course, it's dependent on the kernel function that you use, right? The MMD is always associated to your OKHS, and your OKHS is defined with a kernel function. So if the kernel function that you use is the Gaussian kernel, and you're doing this, the gradient descent over this problem here, you're just doing simple, sorry, I have the bar popping at the bottom. So if you're just doing gradient descent over this minimization problem here over the positions of the blue points, when you use MMD with a Gaussian kernel, you get something that's pretty bad, right? You can use other notions of another kernel, so which defines the energy distance, and it would be using the kernel to be minus the Euclidean distance. And you can see that the results are a bit better. You still have some blue points here lingering at the top, and that don't quite catch these the extremities here, but it's a bit better. Here is what happens when you do gradient descent for optimal transport. It's very efficient, right? The points are matched directly to where they should go. So here's another example, a bit more complicated, where you have to fit 2, your orange point cloud is kind of split in 2. And here's what happens for MMD with the energy distance, so the most efficient notion of MMD for these problems. You can see that it takes a while for the blue points. So the blue points are kind of scattered all over the place, and then it really takes a long time for them to get back to where they should go. While for optimal transport, again, you have something that is very efficient. The points are matched kind of linearly. Oh, sorry, I see that I'm having questions.
Yeah, that was me. Sorry.
Yeah.
Hi, Aude.
Hi.
I wanted to ask you about this. So, so you're talking about doing gradient descent for the location of these points, but does that really make sense to do? Like, do we expect that to even converge? Like,
so
in the sense that
it's not a convex problem. Yeah, of course. So it's not a convex problem, so you can't guarantee that you're going to converge to a global optimum. Yeah, so the quantization problem is a non-convex problem.
Okay, but is there any way to kind of say, like, maybe, I don't know, the optimal transport problem is closer to convex than the MMD problem or something like that? Like,
so so there have been works for trying to understand the gradient flow of MMD and the gradient flow of optimal transport. So the idea would be to show that optimal transport is going to always converge to a global minimum, while MMD tends to get stuck in local minima.
Okay. So you can show that? So it's been shown already? Or?
So no, I think it's more of a conjecture for now. That's something I'd like to prove, because it's in experiments, as you can see, it's fairly clear that something is working better for optimal transport than for MMD. And from what I could see, MMD are very sensitive to initialization, especially with the Gaussian kernel. With the Gaussian kernel, if you initialize really close to the optimum, it converges. But as soon as you're a bit too far, it doesn't work at all. While for optimal transport, wherever I initialize, it seems to work really well.
And is that impacted by your cost function? So obviously, I always think of the kernel as somehow equivalent to the cost function. Probably that's a bit naive, but wouldn't that also depend on which cost you pick?
Yeah, so I think it's the right intuition. And as you can see, MMD with energy distance works much better than with the Gaussian kernel. But we still, I found that for optimal transport, whatever power of the Euclidean distance I used was very efficient, while MMD, like even if I use energy distance and try to choose the best Euclidean distance for that energy distance, it still gets very slow or stuck. So.
Okay, thanks.
Sure. Right, so these little point clouds problem is just a toy learning problem, but the idea is to show you that optimal transport has better gradients. And so it's better in a way at understanding the geometry of your problem and just solving these minimization problems in a more efficient way. And so if you look at this little recap here, you can see that MMD behaves better from a statistical perspective, from a computational perspective, but then optimal transport has better gradients, more efficient at finding the minimizers for these problems. And so ideally, we would want to be able to use some notion of distance that behaves like OT from a geometrical perspective, but then has a better simple complexity and a better computational complexity. And so the solution here that I propose is to use the entropy-regularization of optimal transport. So it was first introduced to the machine learning community, at least by Marco Cuturi in 2013. And so it consists in just taking your Wasserstein distance here, so your minimization problem over couplings, and then adding this entropic term here, which is just the entropy of your coupling with respect to the product measure of your marginals. And so you penalize it with some coefficient here, epsilon. That is going to be the strength of your regularization. And so what does it do in practice, this entropic regularization? Well, it's going to smooth your coupling. So if you recall, the coupling that was a little matrix in my introduction example, here it's just a continuous counterpart, so it's like a curve. When you have a very small regularization parameter, you have something that's very concentrated. So if you want to match a measure alpha on the left to a measure beta at the top here, you just look at the correspondence. And here it's just going to give you pretty much a pointwise correspondence because the coupling pi is very concentrated. But when your regularization increases, you can see that this coupling becomes more diffuse. In the end, it's becoming very blurry and just matches very large areas of your first measure to large areas of your second measure. And so why are we interested in looking at this entropic regularization? So it introduces some blurring bias, but the good news is that it's going to simplify the computations. So for that, you need to look at the dual problem of optimal transport. So if you remember, optimal transport was minimizing over couplings that were constrained to have one marginal alpha and one marginal beta. And so here U and V are the Lagrange multipliers associated to each constraint. And so here U is going to be the multiplier associated to the alpha constraint and V to the beta constraint. And so now you're maximizing over U and V that are continuous functions, this simple linear problem, but that has a constraint that the sum of U and V is smaller than C, so where C is your cost function. So the dual of optimal transport problem is still a complex constraint problem, but if you look at the regularized form, this hard constraint here that U and V is smaller than C is actually replaced by an exponential penalty. So to see that, you just need to do the standard Fenchel-Rockefeller duality, and you obtain this unconstrained maximization problem where your hard constraint from the classic optimal transport problem is replaced by this exponential penalty here that U and penalizing U plus V minus C. And so now your problem is a smooth unconstrained maximization problem over two variables U and V. So an intuitive way to solve this problem would be to alternate between fixing U and maximizing over V and fixing V and maximizing over U. And so this iterative algorithm actually has a name. It's called Sinkhorn's algorithm. And you can show that this alternating scheme converges to an optimum. And in the discrete case, if you write the iterations, they can be written in a very simple form that it just ends up being a sequence of vector matrix multiplications. So you just need to write so instead of directly working with U and V, you work with the exponentials of U and V. Then you encode the cost information in a matrix. And then you're going to do your iterations by just doing these matrix vector multiplications. And so each of these iterations is going to go to n square if you have two measures alpha and beta of size n. And you're going to repeat these two steps until convergence. So this tells you that your Sinkhorn algorithm has a complexity that is big O of n squared, but the key is knowing how many iterations you're going to have to do until your algorithm converges. And so, of course, there's no magic here. The number of iterations that you have to do degrades very badly when epsilon goes to 0. So when you're trying to get closer to the true optimal transport problem, you're going to have to run your Sinkhorn iterations for a very long time until you converge. So for very small epsilon, it ends up being very inefficient. But for large enough regularizations, you have a very efficient algorithm that gives you an approximation of optimal transport in O of n squared, which is much improved compared to the n cube log n from the standard optimal transport, and which compares to the n square of MNT. A nice byproduct of this Sinkhorn algorithm, I'm going to just pass really quickly on this, but it's just a sequence, as I said, of matrix vector multiplications, essentially. So it's easy to differentiate, and you can just write your your approximation of optimal transport with the Sinkhorn algorithm. And if you use your favorite automatic differentiation library, you can just differentiate through this, and it makes it very pleasant to use in learning problem. And you can use it for a variety of optimal transport related problems, such as sorting, clustering, assignments, and of course in learning problems, which I will get back to a bit later. So I just explained how this entropic regularization solves the computational problem from optimal transport. Well, here, the question that I tried to answer during my PhD was how does it improve the sample complexity? So the sample complexity that I already mentioned previously is intuitively how well your notion of distance between measures is approximated by the distance on samples of the measures. So for optimal transport, if you look at the Wasserstein distance between two measures alpha and beta, and the Wasserstein distance between samples of these measures, alpha n hat and beta n hat, then the convergence rate is n to the minus 1 over d, which means that if you want to reach some precision, eta, then the number of samples that you have to take to reach that precision increases exponentially with the dimension. So it's when the dimension of your space increases, estimating optimal transport from samples of the measures is pretty inefficient. On the other hand, for MMD, if you look at MMD between alpha and beta, and MMD between alpha n hat and beta n hat, this convergence rate doesn't depend on dimension. You always get the 1 over square root of n rate. And so the question that we set to answer was what happens when you look at the cost associated to entropy regularized optimal transport, W epsilon. And so the answer is that actually you get some interpolating behavior that is going to depend on the strength of your regularization parameter. So when epsilon is small, meaning you're close to optimal transport, your convergence rate is going to be 1 over square root of n, but with this very bad coefficient here, 1 over epsilon to d over 2, where d is the dimension of your space. So you still have some curves of dimension here, because your convergence rate is going to degrade exponentially with the dimension. On the other hand, when epsilon is large enough, you get a 1 over square root of n convergence rate, which is similar to MMD. So the idea is that if you take a regularization large enough, you're able to break this curves of dimension, and you have a notion of a regularized notion of optimal transport that has a better sample complexity. And so that is going to behave better when you're estimating it from samples of the measures. Okay, so know that we have this nice regularized optimal transport distance. So we've seen that it's efficient from a computational perspective and if also efficient from a statistical perspective. And so we want to see how it works in a quantization problem. And actually, it's not good, right? So we were hoping for the blue point to kind of cover this orange area, and what we get is something that just concentrates in the middle. So what happens here is actually that's the effect of entropy. So if we take epsilon to be small, then we get a solution that covers pretty much the point cloud. But as soon as epsilon increases too much, and so of course, in practice, we would like to have epsilon to be large enough so that our Sinkhorn algorithm is fast. Well, we get something that collapses to the middle of the point cloud. And there's actually a nice paper that explains this behavior. And the intuition behind that is that entropic transport is maximum likelihood under Gaussian noise. So if you take a noisy sample that was generated according to some probability model alpha theta plus some Gaussian noise of variance epsilon, then the MLE for your model alpha theta is going to be the same as the argument of the regularized Wasserstein distance between alpha theta and your data here, where the regularization for the Wasserstein distance is the same as your Gaussian noise. So again, how to see it maybe in a bit more visual way. It means that your estimator here assumes that the data in orange was generated with some noise of variance epsilon. So here it assumes that there was some noise of variance 0.1, so not too much noise. Here it assumes that the noise was much larger, so it's trying to cancel out the noise by concentrating more around the mean. And here it assumes that pretty much all your data was corrupted with noise. And so you see if you actually draw Gaussians of variance epsilon around your solutions here, so you have the solutions in blue, and then we draw little Gaussians of variance epsilon around them. Well, you can see that it covers your point cloud more efficiently. So it's actually just assuming that you had introduced noise in your data set and it's trying to cancel out the noise. So while this can be a desirable future if you know that your data set was noisy and you're trying to kill out the noise, well, it's geometrically not very satisfying, right? Because we were hoping to be able to recover the geometry of our data set and using a large enough regularization so that we're efficient and have a good sample complexity. So how can we get around this effect of entropy that kind of collapses everything to the mean. Well, the idea that we introduced was to use Sinkhorn divergences. And so the very naive idea was just to realize that when we look at the regularized Wasserstein distance between alpha and itself, because of the entropy, it's not equal to 0. And so we just wanted to introduce corrective terms that would debias, in a sense, this regularized Wasserstein distance, so that when you look at this new thing that we call Sinkhorn divergences between alpha and beta, when alpha equals beta, it's going to be equal to 0. So the Sinkhorn divergences here are simply the regularized Wasserstein distance between alpha and beta, minus half of the Wasserstein distance between alpha and itself, and the Wasserstein distance between beta and itself. And you can check very easily that when alpha equals beta, this thing is equal to 0. So that was it's a very simple and naive idea behind the introduction of Sinkhorn divergences. But actually, they have an interesting property, which is that they interpolate between optimal transport as epsilon goes to 0 and MMD as epsilon goes to plus infinity, where the MMD is associated to minus, to whose kernel is minus the costs that you use in optimal transport. And so that's where you really see, as François-Xavier said, the intuition that the kernel function and the cost in MMD and the cost function in optimal transport are really closely connected. And here, to get an MMD that is valid, you need to ensure.
Can I ask a question again then?
Sure.
At this point? So if you used MMD with, instead of the Gaussian kernel minus the Gaussian kernel, would that then solve the problem? Is that what I should be thinking about? Or?
No, so the thing is that you still need to make sure that minus C here is a positive definite.
Yeah, okay.
Yeah, and okay. So yeah, so it wouldn't work for the Gaussian kernel, but what works here is when you use C to be some power of the Euclidean cost, then minus C is a valid kernel, and it's what's called in the energy distance in the literature. And it's actually only a valid kernel when P is strictly smaller than 2. So when you use the squared Euclidean distance, then your MMD here is not valid, it's not positive definite. While for strictly smaller powers, it's a good notion of a valid notion of MMD.
Okay, thanks.
Sure. So right, we have introduced this interpolating notion of distance between optimal transport and MMD, and you can also prove, that's been done by colleagues at ENS, that these Sinkhorn divergences are positive definite, meaning they're always positive and only equal to 0 when alpha equals beta. So it was actually a fairly naive idea at the beginning, but it has two very nice properties. It's actually a positive definite metric, and it's interpolating between optimal transport and MMD. So just here, a little parenthesis to understand energy distance. So as I said, energy distance or MMD when you take the kernel to be minus the Euclidean distance for some power P of the Euclidean distance. Here's what happens when you take P equal 1. So you get something that works fairly well. You still have these little points that kind of lag behind. Like it's the same animation that I showed in the introduction. And here's what happens when you use P equals 2. Okay, it doesn't work at all. So there's really a cutoff when you move to P equal 2. Your MMD, your energy distance, is not positive definite anymore, and so it doesn't work at all. So that's something you have to be careful about. And that also tells you that when you're using Sinkhorn divergences that converge to MMD with large epsilon, you're better off using powers of P that are smaller than 2. Right, so here's what happens for Sinkhorn divergences with epsilon equal to 1. It works really well. When we're using entropy-regularized optimal transport earlier, we had something with the same regularization epsilon. We had something that was really collapsing to the mean. With Sinkhorn divergences, it works much better. And even if you consider the more complicated example here with 2-point clouds, you can see that it works pretty nicely. So it's even the dynamics are kind of interpolating between optimal transport and MMD. If you remember from the introduction on this 2-point cloud example, the MMD was sending points all over the place and then having a really hard time bringing the blue points back to the orange points. And optimal transport was doing kind of a linear assignment. And here, Sinkhorn divergences are doing something a bit hybrid. So it's still scattering the blue point cloud a little, but then assigning points fairly efficiently. So just a summary of the different notions of distance. That was maybe a lot. So here we're just looking at the small quantization problem. When you're using regularized optimal transport, you're here with a regularization epsilon equals 1, which is large enough so that we have very few, so that we need very few Sinkhorn iterations to converge. We have something here that collapses to the mean, but when we use Sinkhorn divergences with the same regularization, so with the same computational complexity, essentially, we get something that works much better. And of course, when we take epsilon to be larger, we start converging to MMD, and we start having points that are lagging behind here. And in the limit, this is going to look like that, like the energy distance. And here I choose a power strictly smaller than 2 to make sure that I have something that is well defined. All right, so know that I have showed that Sinkhorn divergences work well on some toy problems. So here, these quantization of point clouds in 2D. It's time to move to a bit more complicated parametric problems. And here, I'm going to focus on a class of models that are called generative models. So it consists in saying that your parametric distribution alpha theta is defined as the push forward of some latent distribution zeta in some usually lower dimensional space z that is pushed forward through some parametric function g theta, which brings you to your data space x that is usually high dimensional. And so you are going to want to learn your push forward function g theta so that it pushes zeta to so it pushes zeta forward with the g theta, and then you recover the orange point cloud in a nice way. So why do we call these models generative models? Essentially, it's because they're really easy to generate samples from. So to sample a point x according to this parameter to your generative model alpha theta, you first draw a sample z from the latent distribution zeta, and then you take x to be g theta of z, and your data point x here is going to be distributed as alpha theta. So they are really easy to generate samples from, but you don't have usually don't have access to their density, so you can't perform maximum likelihood estimation, and you need to find another way to perform inference without relying on the standard MLE concept. And so the idea that we propose here is to just minimize the Sinkhorn divergence between your parametric model alpha theta and your data distribution beta, where alpha theta and beta are only accessed through samples because beta is your data set and alpha theta is your generative model, which you can only access with through samples. So the idea is fairly simple. We're just going to do gradient descent over the Sinkhorn divergence. And so at each step of the gradient descent, we're going to approximate the Sinkhorn divergence by taking batches of alpha theta and beta at the current iterate theta k. And then we're going to perform a fixed number of Sinkhorn iterations to compute these Sinkhorn divergences. And then once we have this approximation, we're going to compute the gradient by automatic differentiation. And then we do a standard gradient update here. So here's a more visual way of understanding the algorithm with a free French lesson on top. So you have you take a batch from your data here in orange, and then you take a sample from your generative model. So to take a sample from your generative model, you first take a sample from your latent distribution zeta. You pass it through your push forward function g theta, which in practice is often going to be a neural network. And then you have your sample from the generative model. Then you combine these two samples in a cost matrix C. And then you use this cost matrix to run your Sinkhorn algorithm. You run a fixed number of steps. And then this gives you an approximation. So you do it for each terms of the Sinkhorn divergence. And this gives you an approximate distance between alpha, theta, and beta. And everything in this scheme here is differentiable. So if you want to take the gradient of that thing with respect to theta, you can just do it by back propagating through everything until you get the gradient with respect to theta. Right. And I'm gonna wrap up by showing you how this works in a couple of examples. So first, to visualize better, here's a toy example in 3D, which is fitting an ellipse. So in this setting, the latent distribution is going to be the uniform ball over the unit ball in R3. So you're here, the latent space and the data space are both R3. And the push forward function G is going to be, so if you take a point Z in the unit ball over R3, then you're going to push it forward by doing X equals AZ plus omega. And this is going to transform your ball here into an ellipse. And so omega is the center of the ellipse and A is the covariance of the ellipse. And so if we use the previous gradient descent algorithm to learn the parameters of the ellipse, here's what happens when we use regularized optimal transport. So we still have this problem of having an estimator that is shrunk. You can see here a little green line that shows you that your ellipse has completely collapsed to the mean. Again, because it assumes that your data was noisy in the first place, and that instead of an ellipse, you were actually trying to model a line. Whereas when you debias with Sinkhorn divergences, you have something that really recovers the structure of your data. And here's a comparison of the energy distance and Sinkhorn divergence. So here I think so here's energy distance with P equals 1.5, and here it's Sinkhorn divergence with the squared Euclidean distance, but this was the best power for the energy distance. And if you compare the parameters of the ground truth to the parameters of energy distance and Sinkhorn divergence, you can see that the Sinkhorn divergence has a better estimation of the parameters of the both the covariance and the center of the ellipse. Right, so this is a simple 3D example to convince you that Sinkhorn divergences work well, and know you can use it in more complex settings. And in particular, you can learn generative models of images, which are a popular application in the world of generative models. And so the issue when you're working with images is that you can't really use the Euclidean distance as a cost function anymore, because looking at the Euclidean distance between images doesn't make much sense. And so choosing the right notion of cost C can be a bit complicated. So you could choose a cost function that is well suited to images, for instance, by taking the last layer of a trained neural network. But you can also learn the cost function in an adversarial way. And so the idea is that you want your cost to be able to discriminate between samples from your model alpha theta and real samples from your data set beta. So you want your cost to give high values to your Sinkhorn divergence when alpha is not equal to beta. And so when you're going to learn your cost, you're going to maximize the Sinkhorn divergence. So you're parameterizing your cost function as the Euclidean distance over some embedding here. There's, again, going to be a neural network in practice. And so your optimization procedure becomes a min-max. So you're still minimizing over the parameters of your model alpha theta, but now you're also maximizing over the parameters of your cost function. And so here we do this for the Sinkhorn divergence, but this idea of learning the cost function adversarially has already been done for MMD, where they are learning the kernel function in the same way. So here you could replace Sinkhorn divergence and cost function C by MMD with kernel function K phi. And so you recover a GAN type problem where you have to alternatively minimize over the parameters of your model and maximize over the parameters of your discriminator. And C, so the cost function C here acts as the discriminator in standard GAN literature. And so then we can apply it to generative model of images. So here's an example for CFAR. So this, so here we compare to MMD GAN, which was done with Gaussian kernel in a paper by Lee et al. So these results are really a couple of years old, which is very old for GAN paper. So it's not state of the art anymore, far from it. But the goal was still to show that on this kind of task, using entropy-regularized optimal transport, and so in particular, these debiased Sinkhorn divergences, allows you to recover images that have a better inception score than MMD. And so inception score, sorry, is a popular metric for to evaluate generative models. And so that's, let me just wrap up by summarizing the key messages of this talk. So Sinkhorn divergences are a great notion of distance between measures. They are essentially a way to debias the regularized Wasserstein distance, which because of entropy tends to shrink your estimators. But they allow you to interpolate between optimal transport for small epsilon and MMD for large epsilon. And this way you kind of get the best of both worlds. You still inherit the good geometric properties from OT. So you have a distance that has informative gradients and that allows you to solve minimization tasks in an efficient way. But you also break the curse of dimension for epsilon large enough. You recover a sample complexity that is similar to MMD. And most importantly, you get fast algorithm that allows you to use these Sinkhorn divergences in a variety of machine learning tasks, as I showed you for generative models.